So here's the setup I'm using. I've got a 12-volt power supply connected just to, first of all, to a voltmeter. So that's just going to measure the voltage produced by the supply. Now it says it's 12 volts and right now it's producing 11.32. You'll see what happens when we connect in the heater. So then I've got this little circuit here which runs from a coil of wire, which is just nichrome wire wound around a pencil, and that's going through an ammeter which is going to measure my current. So I'll measure the current and the voltage, and I put these in here and connect them across the voltmeter so I know what the true voltage is. And I put the coil in so that pretty much all of the resistance wire is in the water, and I measured out 100 mils of water. I made sure the water was roughly room temperature, and then I've got a thermometer here to measure the temperature. So actually room temperature is 22 at the moment. I think this water was coming in at 25, but it's not far off. The closer it is to room temperature, the better. But ideally you'd have it a little bit less than room temperature. Because the hard thing about this experiment is that you want all of the electrical heat energy, all the energy that's been released, as it were, by the electricity running through the wire, you want all of that to be realized in the temperature rise of the water. And of course, what some of it's going to do is to warm up the can. That's why I'm using a can and not a beaker. I tried it with the beaker, and because this takes more energy to warm it up than this can, it doesn't give such a big temperature rise. We want it all just to come from the water. So this is reading about 24.5 degrees. That's my initial temperature. And what I'm going to do is I'm going to turn it on for 120 seconds. So go. So I've got my watch measuring the time, and we can see that the current is 3.5 amps. So I'm writing this down. I is 3.5 amps, and the voltmeter, remember it was reading 11, now it's down to 9.36, 9.37. And now it's gone off. Gosh, what are you doing? .38. So V is 9.39 right now. So it's fluctuating around that last little decimal place. Not a big deal. So I experimented with different times. If you get it too hot, then what's going to happen is you'll start losing much more heat to the environment, and so it won't be accurate. If you do it for too little time, then there's hardly any temperature rise, so you can't see that. And it's quite a good exercise for students to think about what is going to be the best temperature rise to use. So the watch is ticking away, so I'm going to give this 2 minutes. And it's quite a good idea to stir the water a little bit gently with the thermometer as well, because it'll be hottest at the top and coolest at the bottom where the thermometer is. And when you turn off after 2 minutes exactly. That's what I'm going to do. That'll be 120 seconds. So count down. 5, 4, 3, 2, 1, and turn it off. Now I can see it's reading about 34.5 degrees. I'll just stir it around and see if it gets any warmer. So it's pretty much, it'll still, as the heat gets into the ball of the thermometer and warms up the oil, you might find it goes up a bit more. In fact, I'm reckoning this has gone up to 35 degrees. So it's a good idea to repeat those readings quite a lot. But by knowing we've got 100 mils of water, we should be able to work out the heat capacity of water. Right, I'm going to have a go at doing the same experiment, this time with 100 grams of oil. So rather than use a measuring cylinder, which isn't going to tell me the right amount of oil very easily, I'm going to just use the top hand balance, just going to pour the liquid straight into the can until I get to 100 grams. Can't go wrong. So I'm just using, this is regular canola oil. Just poured just a little tiny bit too much. Alright, that's close enough, I think. Now one more drop out. Alright, so I've got 101 grams. That'll be okay. 100.8 grams. So similar amount of oil, same setup with the coil going in there, same setup with the thermometer going into the oil. We'll wait for the thermometer to get to the normal temperature. And this probably is true room temperature. It's been in the back of the cupboard, so it's been a bit cooler. So this is reading 21.5 degrees. That's 100.8 grams of oil. And get the stopwatch ready. And back to 0, 3, 2, 1, go. Okay, so we'll leave this running for 2 minutes as well, despite what I expect will be a higher temperature rise. So the voltage is 9.41 volts. And the current is 3.5 amps. We're going to give it 2 minutes on the clock. Come on, watch. You can fast forward if you're watching this on a video. But I am doing this live. Come on, watch. Eight, 7, 6, 5, 4, 3, 2, 1, off. Swirl this around a bit. So this is reading, it's gone up to 36, oh, 38 degrees. Oh, it's gone up to 40. Still going up, but I can see everything's turned off. So with the bigger temperature rises, more of a lag, I guess. It's got a 42. And I don't think it's going up anymore. 42 degrees with 100 grams of oil. Kia ora koutou. I'm going to now run through the equations and the calculations for working out the specific heat capacity of water and then oil, which I showed how to measure with just a little bit of wire and a lamp pack. So I've written down the equations which are on the equations sheet. So we've got the equation which involves specific heat capacity, and the energy which causes a temperature rise delta T depends on the mass of the material and this thing called the specific heat capacity. And we put in the energy by using a current going through the wire, and we know the voltage that it was supplied at, so we can work out the power. And from that we can use this equation which tells us how much energy has been transformed, where we've got delta E equals P delta T. So that's the energy that will become the thermal energy which goes into heating the water, I hope. There's two ways of doing this, and usually with a class I would probably take them through going slowly through it. So we'll first of all work out the power that was being provided by the electricity supply, and we had 9.39 volts, and we've got 3.5 amps. So we can multiply those together and get the power in watts. So that's times 3.5, and that came out as 32.865. I won't round it off, but you could really just call it 33. I'll just write 33 watts here, but leave it in my calculator as it is. So now we're going to work out how much energy went in the time of 120 seconds. So notice it's really important the students learn that in physics things are very case sensitive. So little t is time, whereas big T is going to be temperature. So we've got the power, which I'll put down here as 33, but I'll use what's in my calculator, times 120. And so I'm going to multiply this by 120, and it's coming out as 3943.8. So we can call that, I'll write 3944 joules. So that's the energy in joules which is going into the water. Okay, now when we did it with the water, we had a temperature rise, which was, it went from 24.5 to 35. So it's about a 10-degree rise. I've done it several times, and it came out as about 10 degrees every time. That time it was 10.5, but the thermometers are really, the school thermometers, pretty hard to read. So I'll put it in as 10. The mass of the water, I measured 100 mils, so that's 0.1 of a kilogram. And the temperature rise, we've got that, sorry, we know the mass and we know the energy. So now you might want to put in the numbers into the equation as is to avoid the students having to do any rearranging. But I'm going to assume they know a little bit of algebra, and they can divide both sides by m and delta T. So we end up with C equal E thermal divided by m delta T, where we're on a capital T this time. Okay, so we put in the numbers. We've got this number from here, 3944. We're assuming it's all turned into the thermal energy in the water, and we've got the temperature, the mass of 0.1, and we've got the temperature rise of 10. So we've got an answer. This is very conveniently coming out as 1. So this is 3944 joules per kilogram per Kelvin temperature rise. So degree C difference is the same as a degree Kelvin, so this is the official unit. You could put degree C, doesn't make any difference. So this is the value we've made it for water. You could, if you want to, just kind of give them a magic formula for the whole thing, and so it could be C equals VI delta T. So you could just have the power term and the time term and the mass and the temperature rise and just put it all in a magic formula there. Or you could even give them a spreadsheet where it works out automatically. The thing about this, it's got so many terms in it, it's a bit overwhelming. So I would prefer to do it in little bits, and we'll say this is the power, this is the energy which has gone into it, and it depends on the mass and the temperature rise. Here's our answer. So that's the value for water. We'll just do it now for oil. Oil, I measured out the oil, so we had exactly 0.1 kilos again, 100 grams. So I did that by weighing it. And this time, the temperature rise, it went from 21.5 up to 42. Okay. So 42 take 22 is 20 degrees. So I'm going to say it's roughly 20 this time. So we can already see what's going to happen. So we've got a 20 Kelvin or 20 degrees C rise. The specific heat capacity is going to work out. It's still the same equation. And we put in the numbers. This is the same because we use the same circuit and the same time. And this time we've got the same mass, but we've got double the temperature rise. So we're obviously going to get half that value of what we had before, which comes out as 1972 joules per kilogram per Kelvin. What we find, in fact, if you were to do it with other liquids, I can't think of any that are really easily available which you could do super safely. I don't know if I'd want to do it with alcohols. And it would be interesting to do it with mercury, but I'm sure we shouldn't do that. But water has this extremely high specific heat capacity, and this is all to do with the H2O molecule and how it bonds and how it can move around as it vibrates compared with the oil. So oils will heat up much more quickly if you give them the same amount of heat energy, if you have the same input, which is something you need to watch out for if you're cooking, because the fat will get a lot hotter than you expect if you're used to heating up water. You might want to compare these to the book values and see what's on the internet. So I'm looking up heat capacity in this classic ancient physics textbook. All the old textbooks will have this stuff in because we used to teach it years ago. And there was heaps of stuff that was done in the 20th century on heat and temperature. But here's a page on heat capacity in Nelson and Parker. And what you can see is the value they're giving for water is 4,200, whereas down the bottom we've got paraffin oil 2.1. Most of these, and we could try brine because that adding the salt reduces the heat capacity quite a bit. So that's something else you might want to try. So paraffin oil 2.1 that's times 10 to the 3, so that's 2,100. So both our values are a little bit low. The book value is 2,100, and here the value is 4,200 from the book, but they're pretty close, and you can see there's a significant change between the water and the oil. Hope that's helpful. It's definitely worth doing. It's pretty simple, and it pulls together quite a lot of the bits of the energy topic into something that's realistic. Could be used for thinking about cooking, for jug kettles, anything where you're heating a liquid. There's huge amounts of things are heated by resistance wires. So whether it's your washing machine or your dishwasher, and if you just think of all the household appliances that have heaters in, they're just resistance wires most of the time.